Alright, in this video we got a new set of problems on matrix multiplication. Kind of taking a different perspective on it and also doing some matrix algebra with the inverses. So suppose A, B, C, and D are invertible n by n matrices and A times B inverse times C is equal to D inverse. We want to write a simplified expression for B in terms of A, B, or probably A, C, D, and or their inverses. Probably be able to change that. Okay, so this is where we just have to be conscious of the fact that left multiplication and right multiplication are not the same thing for matrices. So we're going to need to do something first to, start getting at B. And it doesn't really matter how you want to do it. If you want to get rid of A and then get rid of C, or introduce a regular B to the right-hand side, I don't think that would be appropriate quite yet, right? Because we're going to want to introduce a B to cancel off with B inverse. But I think I'm going to just start by getting rid of the C. So that's multiplying by C inverse on the right. And so that'll be A times B inverse equaling, oh yes, I remember I had a kind of a message with this problem too. D inverse C inverse. Okay. And then if we wanted to, get rid of the A, maybe we would multiply both sides on the left by A inverse. About like that. And then we would have B inverse equaling A inverse, D inverse, C inverse. And it's like, oh, well, we have the theorem about the product of two matrices, their inverse, but what about the product of three matrices? Like, how is that going to work? And I'm thinking maybe rather than trying to hack through that logically with this, let's just take a different approach to this problem and see what that tells us. Okay, so going with a different approach, maybe rather than just solving for B inverse, I'm going to expose the B inverse, like kind of with the same technique. So I think I had a, what was it? This was the beginning of this line right here. Before I multiplied both sides on the left by A inverse, I had an A times B inverse, and is that what I want to do? Yeah, that's what I want to do. And that's going to equal D inverse C inverse. Okay. Yeah, and then I'm going to want to introduce a regular B that I can solve for and, like more directly by multiplying both sides on the right by B. Okay, so then I'll have A equals D inverse C inverse B. Okay, then I think, if I want to try to get at B, I'm going to multiply on the left by D. And then I'm going to multiply on the left by C. Okay, there we go. All right, so we see C, D, A. And so that's kind of what I had suspected would happen, is that the one in the middle would stay in the middle, and that the other two would kind of switch positions, but I was not sure about that. And I mean, I'm sure we could have like really thought about the way that the theorem worked and pieced through that, using logic, but I think this is maybe a better way of discovering that work. Okay, so number 2, we are having m times m transpose equaling n. Okay, so I need to write out a formula for m times m transpose, and then I'm going to do the multiplication. So 1 plus a squared b plus 2a, b plus 2a again, and then b squared plus 4. Alright, so we're going to say, alright, that means that the 1 plus a squared is going to need to equal the 5, the b squared plus 4 needs to equal the 13, and then the b plus 2a's need to equal 7. Okay, so we're going to have that all here. To be honest, I clearly made an error when I was writing this problem, and there was something wrong with matrix n. I'm not sure what I thought was going to happen, but here we go. This is what we've got. Looking at the kind of two individual equations that are narrowing A and B down to two possible values. The only way I could get B plus 2A to equal 7 would be if B was the positive 3 and A was the positive 2. So I'm going to say A equals 2 and B equals 3. All right. Now, number 3. B equals A transpose A. What is B, the third entry first column? Pardon me, third row first column. All right, and so A transpose A is going to be, all right, well, rows become columns. So 1, 0, negative 1, 1, 2, 1, 1, 2, negative 1, and 1, 0, 0. Multiplying by 1, 1, 1, 1, 0, 2, 2, 0, negative 1, 1, negative 1, 0. All right. So this is going to be, first one is the first column of the result is going to be just add all four of them together, so all four of the original columns together, so 4, 4, negative 1. And the second column will be add 2 of each of the middle columns, so that's 2, 4, 4, 8, and 0. And then we're going to take last column, negative 1 of the first column. I'm going to have to do this one. Plus 1 of the second column. Minus 1 of the third column. Okay, yeah, and I'm going to add those all together. Get negative 1, 0, and 3. All right. Okay. The other one, I did not take the column view of the multiplication because of the variables inside the matrix, and then that's new to us, and so I thought it was better to just kind of do the multiplication the old way. But this one, I think, I want you to really start looking at matrix multiplication as the combinations of the columns, because that will really help when we go to start talking about spaces later on. All right. Now, if Q equals PD P inverse, what is Q to the 3? This is a problem where we're going to have to do some algebra first and make our job a little bit easier. So PD P inverse. Then we're going to notice that those P times P inverses are going to cancel, and so we're going to have P 3 powers of the diagonal matrix in the middle, and then P inverse. I'm going to do a couple of problems off to the side about taking a diagonal matrix to various powers, because d to the 3 is going to be like negative 8, 0, 0, 27. But I think maybe I'll just show you that in action right now. All right, so that's going to be, first I'm going to take the third power of d. That's going to be negative 2, 0, 0, 3. Maybe I'll just start with taking the squaring d. Alright, so then I'm going to take negative 2 of the first column and none of the second column. Okay, so that's going to be 4 and 0. And then the second column will be 0 of the first column and 3 of the second column, so that's 0, 9. And then that means that d to the 3 will equal 4, 0, 0, 9 multiplied by negative 2, 0, 0, 3. And that's going to be, again, negative 2 of the first column and none of the second column. That'll be negative 8, 0, and 0 of the first column, and 3 of the second column is 0 and 27. All right, so I can probably get rid of all of that work. That's showing you that in action. And if you needed more reason to believe me that that's how you work with the diagonal matrix powers, just let me know and I can do some more practice problems, but I think that was enough. That's gonna be P was 1, 1, 0, 1. D to the 3 was negative 8, 0, 0, 27. P inverse hopefully gave us that. And now we're going to say, all right, well, now I think that there might be something else for us to discover. And this is the type of problem that we're going to come back on at the end of the course when we talk about diagonalization. But I think for now we're just going to do this matrix multiplication, maybe the new way. So negative 8 of the first column, none of the second column, 0 of the first column, 27 of the second column. And so we have that, 1, negative 1, 0, 1. Okay, and so if I take, the matrix and I multiply it by the vector right here, 1, negative 1, I'm going to subtract the first column minus the second column. So negative 8 and negative 8 minus 27 more is negative 35. And then 0, 1, that's going to be none of the first column plus 1 of the second column. That's just going to copy the second column. There we go. Okay. That's going to be q to the 3. All right, so for number 5, we've got AB equaling CA, which is this matrix, which is given, which I'm just going to call M. And I'm going to ask you to find B and C. So I'm going to start with the equation AB equals M, and I'm just going to try to solve for B. I'm going to start by multiplying both sides of this equation on the left by A inverse. Inverse M. Okay, and then I'm going to say, all right, well, that's just a formula for B. That's equal to A inverse M. And I've got A inverse right here. And M right here. And so I should be able to do that without too much trouble. All right, if I'm multiplying A inverse times 1 and negative 1, I'm going to subtract the columns. First column minus second column. So negative 2 and 1. And then 2 of the first column, none of the second column, that would be 2 and 4. And then for the other equation, I've got CA equals M. I'm going to multiply both sides of this equation on the right by A inverse to get C on its own, and so that's M times A inverse, and so that's 1, negative 1, 2, 0, multiplied by 1, 2, 3, 1. Okay, add 1 of the first column plus 2 of the second column, and 3 of the first column plus the second column, so 3 plus 2 is 5. Negative 3 plus 0 is negative 3. All right, that's going to be B here and C there. All right, and then this last problem here is just kind of another, drill on the column perspective of matrix multiplication. If you've got it, maybe you don't need to do this one. Okay, but if you're having any doubts still, okay, or trouble executing it, remember that if I'm taking A times X in this case, I'm not going to do this for all of them, and I'm multiplying it by 1, 1, that's going to be 1 of the first column plus 1 of the second column. And so that's going to be 3 and negative 1. But we're not going to need to do all that work for the rest of these. All right. For B, if y equals 1, 0 transpose to the vector 1, 0, then AY is going to be 1 of the first column, none of the second column. We're just going to copy the first. Okay, if U is 0, 1, then AU is none of the first column and 1 of the second column. Just copy the second column. And if we take 1, negative 1, okay, we've done that a couple of times recently. It's going to subtract first column minus second column. Negative 1, 1 would be second column minus first column. Okay, and then Z is 2, 3. That'll be 2 of the first plus 3 of the second. So that's 4 and 6 is 10, negative 2 and 0. Right, there we go. And I think, yep, that's all we've got for this problem set. So that's all for this video. Thanks for watching.